So welcome back everybody to the fifth lecture of wireless communication. In this part of the lecture, we'll continue talking about wireless propagation characteristics, particularly statistical multipath model of wideband fading. So we just talked about narrowband fading, auto and cross correlation of in-phase and quadrature signal components. Then we will talk about correlation and power spectral density in uniform scattering, signal envelope distribution of fading phenomenon, wideband channels and their characteristics. Now, some of you in the first part of the lecture, they came and said, the math here a little bit scary, a little bit complex, and we don't like this kind of characterization for the channel. Wouldn't you offer us something much simpler? So this is what we are going to do in this part of the lecture, specifically to address that fear that you have about the previous kind of modeling. In fact, this is the first type of modeling that was available mostly in most of the books and this and that. But recently, a group of researchers have come up with another model that can simplify things a little bit more. We'll try to touch upon that model, explain it to you simply, and try to explain it in a way that you link the previous model that you said it's hard with the new model that's going to be hopefully easy. And it might make more sense to you than the previous one. Some of you might be comfortable with the previous model, some might like this model more. We will call this model delay Doppler. We'll talk about it, but just this is since it's an introduction to the lecture. Yes?
Should we remember the equations?
Yeah, the equations, they are, yeah, because they are very simple equations. Those are the simplest equation you can see in wireless communication. They are just representing amplitude, phase, and delay spread, and physics equation, frequency with lambda equals c, frequency with a Doppler frequency with lambda equal velocity multiplied by cosine. These are basic knowledge. And not difficult. I'm saying this is the summation. Why don't you need to remember this? The signal you receive at the receiver is the channel is characterized by the summation of all the paths with different amplitude, different phases, different delays. Such a simple equation. You don't need to memorize it, it's already understandable, I mean, but you need to just train yourself for that. So this is what we talked about, random multipath model. This picture explains the multipath phenomenon, and we have the channel impulse response that we talked about in the first part of the lecture. We have many multipath components, amplitudes change slowly, phases change rapidly. For delay spread, we said that delays when this is narrowband. We said this is narrowband. When delay spread is less than 1 over b, the bandwidth of the signal, we have narrowband communication system. We don't have delay spread. Yeah, we said this, yes? I mean, you just have fading, fluctuation on your signal. If you are having multipath and the delay spread of your channel less than the duration of your signal, you just have fluctuation on your amplitude, which results in fading, but you don't have time distortion. Yeah. And this is the other formula that represents the received signal, the real part of it, and we can conclude that there is no signal distortion in time. Multipath yields complex scale factor in brackets. This is the multipath you have. Simplified, no delta. There is no, this term is not there. When this term is not there, you have narrowband. You don't have delay spread. So what else for you when U is this, the input signal, something like this, your received signal can be written in terms of the in-phase and the quadrature component, and we said the in-phase gets multiplied by cosine and the quadrature by sine. In-phase, and this theta phi 0 is corresponding to the input phase of your message signal, or symbol, data symbol we call it. In phase and the quadrature signal components can be written then like this after they are received at the receiver in terms in narrowband, of course. This is due to the multipath, and this is your carrier. So at the end, the phase we explained that depends on the input phase of your signal, the direction of arrival of your signal, and the delay, the time it takes to reach your receiver. When n large, I and Q jointly Gaussian by central limit theorem, received signal characterized by its mean autocorrelation and cross correlation, and we said when phi n is uniformly distributed. Uniformly distributed, how do you draw this? If I tell you draw this, you have the x-axis here. Let's say this is the x-axis, and this is the y-axis, and you have here the phases. From all the phases from 0 to 2 pi, uniform distribution means they have the same probability. The probability that you receive your signal with phase 0 is the same as the probability of receiving your signal with phase equal pi over 2 or 2 pi. This is what I mean by uniform distribution. If phi n of t uniform in phase quadrature component are mean, they have mean 0, they are independent and stationary, and we call this White sense stationary process. White sense stationary process means that we have mean equal to 0 and autocorrelation independent of the time, just function of tau, function of the time difference, not the instantaneous time. Cross correlation of in-phase quadrature signal can be given like this, which we explained in the previous part of the lecture. In that sense, the cross correlation at 0, if you calculate the cross correlation at 0, you will find that it's 0. Why? Because when you substitute here 0, sine 0, 0, the result is 0. If the cross correlation at tau equals 0 is 0, this means there is no correlation whatsoever between these two signals. What does this imply? This implies that the two signals are independent of each other and orthogonal. Sine and cosine, they are orthogonal. Actually, this makes sense because when they are exactly on top of each other, there is no any similarities between them. And this actually matches with the fact that sine and cosine by nature they are orthogonal to each other. Autocorrelation of received signal is the received signal by the autocorrelation of it, the in-phase component minus the correlation with the quadrature. The in-phase minus the correlation with the quadrature. Since they are orthogonal to each other, they don't have any correlation with each other, so you are left with the quadrature. Thus, R of t is stationary. That's why we say White sense stationary. Mean 0, autocorrelation does not depend on instantaneous time, just depends on delta. And if the autocorrelation at tau equals 0 is 0, this means that they are independent, orthogonal. Under uniform scattering, in-phase and quadrature component have no cross correlation and autocorrelation. Yes? Under uniform, they have no cross correlation, and the autocorrelation function is given by A or in-phase of tau is equal to the quadrature component autocorrelation of tau, which is equal to the received power multiplied by J0, which is, we call this donates like a Q function. This is Bessel function. Also, it's a numerical function. There is no integration for it. That's why they write it in this form, J function. You either take it from curve or from a table. 2 by Fd tau. Fd is the Doppler frequency and tau is the delay. So decorrelates, we find that at d equal to 0.4 lambda, the autocorrelation, which is the Bessel function, Yes, since the autocorrelation is written in terms of Bessel function, the Bessel function, when you say any information about its Bessel function, applies to the autocorrelation. Bessel function has 0, its value is 0 at this distance. What does this mean? This means that this and this, their autocorrelation is 0 at this distance, which is roughly half wavelength. That's why we say that the signals decorrelates, becomes independent of each other if they are separated from each other by half wavelength. If they are separated from each other by half wavelength, they are independent. What does independent mean? You get new observations for your signal. Let's say I'm standing at this position and my system is operating at frequency equal 900 megahertz. When I move 900 megahertz, what's the value of lambda at 900 megahertz? How do you calculate it? We said F lambda equal C. What's C? 3 multiplied by 10 to power 8 meter per second. What's the frequency that I gave you? In the exam, you must be able to define and calculate this. If I tell you at which distance you will get complete decorrelation, at which distance, or in another words, I can say at which distance you will get different observation, exactly like the previous sentence, decorrelation. F, I said, is 900 megahertz. 900 megahertz, 9 multiplied by 10 to the power 8. So this with this goes 3 over 9 third. Third of a meter, lambda is equal to third of a meter. Third of a meter, how much? 33 centimeter. Half wavelength, how much? 16 centimeter or 15. So I must move by 15 centimeter so that I can get another observation which has no relationship with the previous one. You get it? So at this point of when you are here, and this is my phone at 900, I'm at this position. If I move my phone by 15 centimeter, most probably I'm going to receive a complete different observation of the signal, which has nothing to do with this. You understand this concept? Depends on your application. If security, for security, this is good, because my authentication system is based on location. I just want my data to be received at this location. What if you want to decrease the decorrelation system? Decrease the distance of decorrelation. What do? You increase F. If you increase the frequency here, come with me, instead of 900 mega, you use 9 giga, let's say 60 giga. When you divide 3 over 60, becomes, the decorrelation distance becomes in millimeter, 5 millimeter. That's why we call it millimeter wave. Millimeter wave coming from this concept. At giga frequency, the length of the wave in millimeter, like 5 millimeter, 2.5 millimeter. So half wavelength means 2.5 millimeter. So this, if you cannot see the movement in your eye, you get a different channel response. This is how it works in practice. Yeah, will affect the security there much better, because if any movement, you cannot, the one who will hack you, the one who will get your signal from you or access your signal, he must be exactly in your location. Can anybody comes to you and hit you like this, push you and put your phone exactly in your in the location of your phone? With any misalignment, you will not. But if you are operating on 500 megahertz or 50, let's say 100 megahertz, the decorrelation distance is large. So the person can be behind the wall and still the channel seems the same. So this is how you can link things together. Decorrelates over roughly half a wavelength. This is from where we get it from math, the math you hate. We just brought some amazing conclusions. So math is good, teaches us, surprises us with good information. That's why we teach you math, because when you link it with physics, it really surprises you. But if you take it like just variables and know how to solve, but you don't know the meaning of it, then it's not gonna be too much useful to you. So the Bohr spectral density, how do you find the Bohr spectral density? The Bohr spectral density is the Fourier transform of the autocorrelation function. So this is the autocorrelation function. You found it like this. Take the Fourier transform of this, you get the Bohr spectral density. Bohr spectral density is something that shows you the density of your signal, the density of the power of your signal in the frequency domain. So at Fc, what's the value of your signal? At Fc plus D plus minus D. So it gives you another observation for your signal, but in a different domain. So when you take the Bohr spectral density of this, you get this value. Quarter SRI, S stands for Bohr spectral density. F minus Fc, which is this, and this plus Fc, which is this, because when it's minus you go to right, when it's plus you go to left, and this basically this one is Fourier transform of this value, and this value. This is function. Is that clear? The Fourier transform of the Bessel function, which is the autocorrelation function, is equal to the Bohr spectral density, and then you plot it. Of course, these things can be visualized much easier in MATLAB. This is theory. So the signal envelope distribution, we said that we have fading. Yes, fading. When you have multipath components reaching the receiver at the same time, can happen destructive or constructive addition. The central limit theorem approximation leads to Rayleigh distribution in certain cases, depends on the environment, of course. What's the Rayleigh distribution? It's something like this, which looks like Gaussian, but not really, with some differences. But this is basically the distribution of the amplitude of your received signal, which is the sum of all the reflected signals that are reaching at the same time. Clear? What does this mean? Since they add up randomly, yes, they add up randomly, you get a random model for them. Random model, it's not like deterministic model. You define it with a probability, with BDF, probability distribution function, the one you studied in signal and system or in probability and random statistics. So when line of sight component is present, when there is line of sight, now when I'm standing here on my phone with my hand, do I have line of sight with the base station? I don't. There is no line of sight again. Or if I get line of sight, the line of sight will be weak. All of them, most of them get of reflections. Reflections of the buildings, of the objects in the environment, and I get my signal. So this is the modeling of that. This is the modeling. Of course, we have software that we can, for example, get random values, put these values in the software, and the software automatically gives us the closest random distribution model to this data. If you don't want to do it manually, any data, give me just data. I can tell you what's the model of that data. I have like 20, 30 different distribution models. It's like fitting, but not deterministic fitting like the one we studied for path loss and shadowing. It's for random. Fitting is very commonly used in most of the areas you need, because at the end of the day, even the ones who are studying business and community, they do surveys, yes, and they have some parameters. They need to put these parameters in the x-axis and call them independent and dependent parameters. You need to write the dependent parameters in terms of independent parameters. How? You say this person has checked this answer, right? This answer, this answer. You just put them on a curve and they try to fit this with a model. So it's a mathematical concept applies everywhere, not in computer, in communication, in electrical, in business, in economy, in politics, in all the domains. So it's really good to understand how to do it. Like I really used to do it for many of my research, you must be able to do that. Simple exercise on MATLAB, if you search fitting, will teach you how to do that. Measurements support Nagagami. See measurements data, and after you find its model, you found it's Nagagami. In some environments, Nagagami is like Rayleigh but more tense, fading, like with different values. Like Rayleigh fading with parameter equal 1, but here you have fading with m equal 0.5. When m equal 1, Nagagami and Rayleigh, they are equal. You don't get confused by the names. All of them names for models. You don't need to worry about. But each model has different parameters, and accordingly you get different shape. But the concept is the same. You have data, you modeled it by fitting methods, and you get that model. And you need to, after that, the error differs, the outage probability differs, your performance differs, everything. Because everything is based on that, on your channel model. So, up until now, we are talking about narrowband. This is the fading thing I talked about in the previous lecture, when all the signals reach on top of each other. Now, wideband channel, what happens to wideband channel? We said the narrowband delta tau, which is the delay spread, less than the duration of the signal, which is 1 over the bandwidth of u of t. U of t is your data symbol. When delta tau, which is the bandwidth, the delay spread of your channel, greater than the duration of your symbol of your transmit signal, then you have wideband channel. You have delay spread. And see here, all of your reflections are reaching within the window of the receiver. So the receiver cannot distinguish them whether this is reaching at a different time. Sums all of them together randomly, and that's why we get this random model. Here, they are resolvable. The receiver can see this alone, and can see this alone, and can see this alone. Now each tab here composed of multi-path components reaching at the same time. Each one has fading, which can be modeled like this. But also, since there are tabs which are reaching the receiver at different times, you get delay spread. And what's the condition for it to happen? The delay spread is greater than the symbolic duration of your signal. In other words, the bandwidth of your signal is greater than the coherence bandwidth of your channel. Coherence bandwidth, we call coherence bandwidth, CB, coherence bandwidth. The range of frequencies over which your channel doesn't vary much. When your channel varies, starts varying, starts decorrelating, we call the coherence bandwidth of channel finishes, like ends here. We should consider that. So we have one single condition for that to happen, but that single condition you can state it in different words. I can say that delay spread happens when the delay spread happens when the delay in the channel greater than the symbol duration, or when the bandwidth of your signal greater than the coherence bandwidth of the channel. Both are the same, but different way of saying it, because they are based, these two sentences are based in different perspectives, which is based on physics actually. Yes?
Does delta T1 equal delta T2?
Not necessarily. Can be different, because it depends on the environment. See here, where is this? We were putting, see this here. This building produces rays, multipaths, reaching at the first tab. All of them at the first, at last tab. This is at the tab before. So the distance depends on the distance of the object from the transmitter and receiver. This determines delta T. You get it? So now let's take the other way around and see whether we can simplify the understanding of this channel more. We talked about only the delay spread. We didn't talk about Doppler. Doppler happens when your symbol duration is larger than the coherence time of your channel. Let's understand it from a different point of view, different perspective, which is called the delay Doppler impulse response. Now, what we were studying up until now, we call it time varying impulse response. Time varying, how do we model time varying impulse response? We have tau and t, function of time. We call this time varying impulse response. Now, instead of this, we will study another model called delay Doppler impulse response. Both of them for the same purpose, to understand the characteristics of the channel, but one of them make it easy for understanding the behavior of the channel and links it to the physics of the environment in a much clearer way. Like in certain cases, by the way, 1D, the previous model we call it 1D. This model, delay Doppler, we call it 2D because it captures the delay spread and Doppler spread simultaneously in the two domains. There are cases where system designers who are working in companies like Huawei, Ericsson, Nokia, Samsung, Qualcomm, Apple, the ones who are designing receivers and the transmitter and communication components and equipment. System designers abandon the use of tau of t, which is the time varying impulse response, which is less useful sometimes, complex, not easy to understand, and instead they parameterize the channel via its delay Doppler response. So the difference between this and this is the new model, we call it 2D model. And this is the previous model, we call it 1D. This, we claim that it's much easier to understand and maps the physics in a much easier way to understand. The delay Doppler impulse response the parameters that he uses, the parameter that the model uses to characterize itself, just the delay and Doppler V, which reflects the speed actually, which is related inherently to Doppler frequency. The delayed Doppler impulse response has an appealing physical interpretation. For every point tau V